Happy Wednesday. This is lecture number 28. We're going to be discussing section 4.5, optimization, some more. First, I want to start with some leftovers from section 4.3. 4.3, we were discussing derivatives and the shape of graphs. In that section, I guess it was in that section, we learned the first derivative test for local extrema. If f prime changes sign at some x value, then that's the location of a local max or local min. What I didn't discuss when we were discussing section 4.3 was another test called the second derivative test for local max and mins. So that's meeting part 1. So let me pull up that test. Second derivative test says if there's some x value where the first derivative is 0 and the second derivative is positive, then that tells you that there's a local min at that x value. So for instance, here is a graph where there's a place where the first derivative is 0 because the slope of the tangent line is 0 at x equals c. And also the graph is concave up. So we can see that there's a min. And then there's another diagram, of course. If you flip that thing upside down, you'd still have a tangent line that's horizontal, but the second derivative would be negative because the graph would be concave down. Such a place would be a local max. Now, it's possible to have the first derivative be 0 and the second derivative be 0. And you might think, well, then there's neither a max nor a min. But you can't actually conclude that. The second derivative test doesn't give you any information about whether there's a max or a min in the case where f prime is 0 and f double prime is also 0. So to give you a better feel of these two tests, I want to do an example where I pull out a bunch of functions and see how they do on these two tests. So in this example, using the first and second derivative tests. I'm going to have a bunch of functions. So in the first column, I'm going to have f of x, and then I'm going to have a column for f prime of x, and then I'm going to have a column for f double prime of x, and then I'm going to have a column for f prime at 0, and I'm going to have a column for f double prime at 0, and then I'm going to have a column for conclusion from the second derivative test. Okay, everybody buckle up because I got a bunch of functions here. They're all pretty simple though. I've got y equals x squared. I've got y equals minus x squared. I've got y equals x cubed. I've got y equals x to the fourth. And I've got y equals minus x to the fourth. All right. Well, these derivatives are easy, so I'm just going to write them down. 2x minus 2x, 3x squared, 4x cubed, minus 4x cubed. Those are all the first derivatives. And then let's look at the second derivatives. They're going to be straightforward. The second derivatives are 2 minus 2, 6x, 12x squared, and minus 12x squared. Now let's see what happens when I substitute in x equals 0 into those derivatives. Well, you can see every one of these things will become 0 when I substitute in x equals 0. So I can just put zeros in all of these places. Now look at f double prime when I substitute in x equals 0. These three things become 0. But the first two don't become 0. They just, 2 and negative 2 are their values. And so notice that's positive, and this is negative. So the second derivative test tells us since f prime at 0 is 0 and f double prime is positive, that tells us there's a local min at x equals 0. Second derivative test in this case tells us since the first derivative is 0, second derivative is negative, tells us that there's a local max. All three of these cases, the second derivative test doesn't tell us anything. If the first derivative is 0 and the second derivative is 0, you don't know. So these are all question marks. So again, you probably want to say, well, can't we just say there's neither a max nor a min? Well, no, we can't say that. The test says you can't use this test. Well, remember we have another test. I projected two tests. I projected the first derivative test, and then I projected the second derivative test. Remember, the first derivative test involves finding the places, the x values, where the first derivative is 0 or discontinuous, and then testing to the left of that important x value and to the right of it to see how the first derivative is changing as you go across that point. So we need to check an x value to the left of x equals 0, and we need to check an x value to the right of x equals 0. Check as in find out what's happening with f prime. So let's do f prime at x equals -1. Let's, just for reference, I'm going to copy that column that's f prime at 0. We already know that column is just full of a bunch of zeros. And then let's check f prime to the right, f prime at x equals 1. Okay, so we're going to plug -1 into each of these formulas. When I plug -1 into here, I get 2 times -1. That's -2, so that's negative. When I plug -1 into this formula, I get -2 times -1. That's +2. That's positive. When I plug -1 into this formula, I get 3 times -1 squared. Oh, that's positive. When I plug -1 into this formula, I get 4x cubed. Oh, yeah, this formula, right, 4x cubed. I'm looking at the wrong formula. 4 times -1 cubed, that's going to be negative. -1 cubed is going to be -8. I'm sorry, -1 cubed is going to be -1. Times 4 is going to be -4, so I'm going to get a minus answer. Now in this case, -1 is going to be cubed, so that's going to be -1 times -4, so that's going to be positive. Now let's go through all these again, but this time plug in x equals 1. This is going to turn out to be positive. This is going to turn out to be positive. I'm sorry, positive, and then this one's negative, and then this one's going to be positive, positive, and then negative. So let's think about the conclusions that we can draw from the first derivative test. Well, the first derivative changes from negative to 0 to positive. So the function changes from decreasing to horizontal tangent line to increasing. So there's a min, local min at x equals 0. Okay, well, we already knew that. In this case, the first derivative changes from positive to 0 to negative. So there's a local max. Again, we already knew that. Now, if you think about the graphs, the graph of the first function is a parabola facing up. The graph of the second function is a parabola facing down. So it makes sense. But the third function, y equals x cubed, the first derivative changes from positive to 0 back to positive. So there's neither a max nor a min. So that's very different from saying I'm not sure. Second derivative test says I don't know. First derivative test says there is definitely not a max or a min. And if you look at the graph of y equals x cubed, it looks like the snaky thing that you make with your arms when you're trying out for the cheering squad at the math academy. Neither a max nor a min at x equals 0. But look at these two other ones. The first derivative changes from negative to 0 to positive for this function, so there's a min. And the last function, the derivative changes from positive to 0 to negative, so there's a max. And that makes sense. If I make a graph of y equals x to the fourth, it looks like that. It looks kind of like a parabola, but it's sort of more flat. And if I make a graph of y equals minus x to the fourth, it's that thing turned upside down. So it's possible to have f prime be 0 and f double prime be 0, and for there to be a local max or a local min or neither. So that's why the second derivative test really cannot be used in this case. You have to go to the first derivative test. So those are tests for local extrema. Now remember what I said, back when we first started discussing extrema, we discussed absolute maxes and absolute mins, and we only found those in the case of a function that's continuous on a closed interval, and we used the closed interval method to find absolute maxes and absolute mins. We didn't have to check, all we had to do was find the places where the derivative was 0 or undefined, and check those places and check the endpoints, and we just compared the y values. We didn't check anything about whether the first derivative was positive or negative. We didn't check the second derivative. We just made that list of important x values, and we got the list of corresponding y values, and we were able to pick out the max value and the min value. But when we turned our attention to local extrema, we had stuff like this. We had these tests that would find local maxes and local mins, but not tell us about absolute maxes and absolute mins. And so now in section 4.5, we're doing optimization. And I said optimization problems are absolute max min problems. And the intervals are not closed intervals. So we're going to have to grapple with this. We're grappling with this idea that we don't really have a specific tool, an absolute max min problem, for situations where we don't have a closed interval. All we have are these local max min tests. So what we have to do in this section on absolute extrema is we have to use those local max min tools to find local max mins, but then we have to do this thing. We have to think about what we can say about the shape of the graph and argue that, oh, actually this local max or this local min is actually an absolute max or an absolute min. But it takes some thought to be able to do that, to be able to take that local max, local min tool, find a local max or local min, and then explain why that thing is actually an absolute max or an absolute min. So that's hard. It takes some sophistication. So meeting part 2, I'm going to do something that I almost never do. That is, I'm going to revisit a problem that we did, and I want to finish it a little bit more slowly. So I'm going to revisit the box problem. So we have a box with open top, square base. Must have a volume of 32,000 cubic centimeters. Find the dimensions that minimize the surface area. All right, well, remember what we did on Monday? We got two equations. First of all, we have this picture of the box. So we have x, and we have h. We have two equations. So we have the volume, which is x squared h, and that's known. That's 32,000 centimeters cubed. And then the surface area is, well, the area of the base, which is x squared, plus 4xh. And we need to minimize surface area. Okay, well, what we did on Monday was we used the first equation to eliminate h. So we get h equals v over x squared. And I'm going to put my money where my mouth is. I'm always telling you, don't plug the numbers in until the very end. I'm actually never going to plug the numbers in. I'm just going to use v. Work with letters. Don't plug the numbers in until the very end. So there's my expression for h. I'm going to substitute that into the surface area equation. So we have SA equals x squared plus 4x times v over x squared. Now let's simplify that. Surface area is x squared plus 4v over x. Notice we can see what these two things are from. This is the area of the base, and this is the area of those four sides added all up. Now, our goal is find the x and the h later that minimize surface area. That is the absolute min. Now, what's the domain? Remember I said, life was simple when we were finding absolute max mins on intervals, on domains that were closed intervals. Well, what is our domain? What are the values that x can have? Or let me start with this. What are the values that x cannot have? Yeah.
If not have 4 times volume.
Say it again?
Not have 4 times volume, 4v.
I'm just looking at this equation. for this equation, yeah.
Can't have 0.
Can't have x equals 0. And what else? So that would mean that the good x's are all real numbers except 0. But you can't have a negative x either because we're talking about the length of a side of a box. So we can't have a negative length. So the domain is all x greater than 0. So we have an equation. We're trying to find the absolute min on an interval that's a bummer. It's not a closed interval. Now, remember I said we've got some tests for finding local maxes and local mins. First derivative test, second derivative test. But those involve some work. And as I said earlier, if you do that work, you still haven't found the absolute max, the absolute min. So it helps to think about the absolute max min before you do any work, so you know what you're expecting. Now, a really important thing to do when you get an equation, kind of like when you give a kid a bike, they want to see, well, let's see how fast this will go. Let's see what extreme things we can do with this. Let's check out the extremes in this domain. So in other words, this is a function whose graph, I don't know. I know what a graph of x squared looks like, but that's not what this is. This is weird. So let's think about the extremes. In this equation, what will happen to surface area when x gets very, very close to 0? What happens to the value of this thing when x gets close to 0? Yeah. Yeah, so as when x gets close to 0, surface area goes to infinity. Cooper, you had your hand up. What happens at the other extreme when x goes to infinity?
Surface area approaches 0.
No, that term approaches 0, but this is the equation for surface area. The whole thing.
It's also going to.
Yeah. That makes sense because when x is 0, approaching 0, that means this term is getting huge. That's because you've got a box with a really small base to enclose enough water or enough volume. It's going to have to get super tall. You're going to have a lot of surface area on those sides. This makes sense because when x is huge, that means you've got a box that has a really large base. It's going to have very short walls because it's only allowed to have that volume V. But that's a lot of cardboard, that base. So we've got these two competing things. So notice also that this surface area equation is continuous. There's no funny stuff here. So when you get an equation or a function, you probably are not in the habit of thinking about domains. But think about the domain of the equation you've been given. When are you allowed to use it? And then ask, what happens when I push this thing to the extremes? So we can we know that the surface area graph blows up. It gets really, the surface area goes to infinity when x is close to 0. And we know out here, the surface area also blows up. In between, I don't know. But it's got to be continuous, so, maybe it does this, I'm not sure. But there's definitely going to be a lowest spot, for sure. There might be more than one local min. There might be some local maxes, but there's definitely going to be a local min and an absolute min. So it'll have a local min that is also the absolute min. It's going to have a low spot. It may have some local maxes, but it's not going to have an absolute max. Okay, so remember what I said. Think about what you're expecting before you do any work. Now we're going to go fishing. We're going to go find the local maxes and mins, find out where they are, and that's going to be one of those places is going to be the place where the absolute min occurs. So the strategy is to set SA prime equal to 0, solve for x. And then, I don't know. It's the Wild West here. I'm not sure what we're going to find. We'll have to sort of think our way out of that situation when we get to it. Then wing it. Well, so the result is surface area prime equals 0 only when x equals 9, I'm sorry, looking at the wrong, looking at the cone, only when let's see, surface area prime, so SA prime, that's going to be 2x minus 4v over x squared. And so that's got to equal 0. So I get x cubed equals 2v. So x is the cube root of 2v. Oh, there's only one x value that causes s prime to be 0. So it's not this wacky. So that tells us that the surface area graph looks like this. This happens at x equals the cube root of 2v. So that's where there's a local min and an absolute min. So no more work than finding a local, actually less work than finding a local min, because all I had to do was find the derivative and set the derivative equal to 0. I didn't have to think about, well, is this a local max or a local min or neither. I know it's going to be a local min because there's got to be at least one local min. That's the only place where anything is happening. That's got to be it. So that's what I was saying earlier about you really want to think about what you're expecting before you do any work. So that was meeting part 2, the box problem. Meeting part 3 is farmer building a fence. Or building an enclosure. So it could be something like this, building an enclosure with fences. So it could be this kind of thing. Maybe the farmer is going to make a big rectangular pasture and maybe subdivide it into smaller pastures. Or maybe the farmer is going to put a pasture along the streams so the cows can get to the stream, so the farmer only has to fence 3 sides of the pasture, but making it a rectangular enclosure. So there are 2 types of problems. One is, given a required area, find the dimensions that minimize the length of fence. So given a required area, find dimensions that minimize the total length L of fence. That's type 1. Type 2 is, given an amount L of fence that's available, find the dimensions that maximize the area. Well, I'm going to do a problem of type 2 today. And there's also a problem of type 2 as an example in the book. Gabriel, is that the recorder complaining? All right. So a farmer with L feet of fencing available. Remember, I'm always bugging you to not plug the numbers in until the very end. This time I'm not even going to give you the number. I'm just going to say there's a number L. That's the amount of fence that the farmer has. Needs to build 4 enclosures together like this. So I don't know. Pigs, chickens, cows, snakes. So find the dimensions that maximize the total area. Well, the dimensions I want to think about is this x and this y. So I have a length equation. Which is L, that's how much fence the farmer has. That's got to go into fencing this whole length that's X, and this whole length that's also X, so 2X. And then there are 5 of these babies, 5 things that are of length Y. And then the area equation A equals XY. And we want to maximize A.
Is it for the entire enclosure or just?
Maximize the total area.
Okay.
Okay, so let's use the given length equation to eliminate y. So we have 5y equals L minus 2x. So y is going to be L minus 2x over 5. We're going to substitute that into the area equation. I'm going to do that over here. So A is going to be x times L minus 2x all over 5. Now I'm going to write this in a few different ways. This can be written as, pull out the 1/5, and I have x times L minus 2x. Or I can also write it as, oh, this could be 1/5 out front. Could also be 1/5 times, let's see, I'm going to have minus 2x squared plus xl. What's the domain? This is a cool one. What's the smallest x could be? And could it actually be 0? Actually, yeah, the farmer could make a boneheaded enclosure. You could actually have, I mean, you just pretend, we could have x equaling 0. So how would that look? Well, let's see. I'd have 5 lengths of fence. I can't draw them on top of each other, but there are 5 lengths of fence here. So x is 0 and y would be L over 5. And the area of that enclosure would be 0. Because these are all actually lying right on top of each other. You could also have, well, what's the other extreme? What's the biggest x could be? You look like you know. Yeah. Well, how much fence have we got? We've only got L amount of fence available. Can't be the L because you got to go there and back. So we could have x equal L over 2. So that would look like this. I use half the fence to go out, half the fence to go back. And my y is equal to 0. And so then in this case, my area is equal to 0 also. What's the shape of the area graph? Parabola facing down. So we know that the parabola, the area graph is a parabola facing down, and we know that it's going to cross, it's going to have an x-intercept when x equals 0, and it's going to also have an x-intercept when x is L over 2. Okay, so we're trying to find the value of x that maximizes A. Well, we can see there's going to be one. We're going to find the place where A prime is equal to 0. There's only going to be one. That's going to be a local max, but it's also going to be an absolute max. It's going to be the absolute max. So the strategy, set A prime equal to 0, find A. Find x. Really cool that, you know, if you think about the equations in their extremes right away, you can save yourself a lot of work. So I don't have to test once I find an x value that causes a prime to be 0, I don't have to test it in any other way. I don't have to confirm that it's a local max or local min. I already know I'm going to have a local max that's also an absolute max. All right, meeting part 4. Killer problem. We want to make a paper drinking cup. A conical paper drinking cup with a volume of 27 cubic centimeters. Find, so it's going to be this kind of thing. I'm going to make it yellow. Find the dimensions to minimize the surface area. So what do you mean dimensions? Well, let's call this R and let's call this H. Well, we're going to get two equations again. We're going to get a volume equation and a surface area equation. So the volume is V, and that's 27 cubic centimeters. And that's going to be 1/3 pi r squared h, and the volume of a cone. Surface area is going to be harder. I'm going to call it SA. Now, anybody play Pac-Man? All right, Pac-Man's yellow, right? So we're going to make this cone by taking a disc of paper, and we're going to cut out a wedge, and then we're going to glue it up. That's going to be our cone. So that yellow area is what we want to minimize. And I'm going to call it SA, colored yellow, because I can. So we got to get an equation for that area. Now this yellow surface, this yellow region is enclosed in a larger, is enclosed in a disc. So we have this going on. It's actually part of, you know, we could think about taking a big white disc, cutting out that wedge, and then gluing it up. Well, what's the area of that white disc? Well, I need to know this length. I'm going to call this capital L. So the white disc, the large disc area, is going to be pi times L squared. Well, shoot, what's L? L is going to be this L, and that's going to be this length. L is the slant height. And you see that it's square root of r squared plus h squared. So go back over here. and pi times, well, I'm just going to leave that, well, r squared plus h squared square root, and then that's being squared, and so it's going to be pi times r squared plus h squared. That's the large disk area. But that's not the area that we're after. We're after this area. Now the key to finding that area is to think about the perimeter. So in other words, if this thing were closed up, then the circumference of that yellow disk would be the same as the circumference of the white disk, and they would have the same area. But if this thing were open like all the way to a semicircle, then that semicircle would be half of the length of the whole circumference of the circle. So if I can figure out this length, figure out how it compares to the circumference of the whole circle, that will give me a proportion. That will tell me how much of that area I have here. I hope that makes sense. So this yellow length here, that's the rim of the drinking cup. That's what we're looking at here. This circle with the minus a little arc, that is this circumference. So that circumference C is 2 pi r. So this yellow length is 2 pi r. But for the whole circle, the circumference is 2 pi l, because I've got a circle of radius l, and so that's this white circumference. So this yellow length divided by that white length tells us about the how much of the whole disk we have. It's in this fraction, 2 pi r over 2 pi l. In other words, just r over l. That's the portion of this whole disk that we have colored yellow. If r is the same as l, then we have the whole disk is yellow. If r is 1/2 of l, then I've got a semicircle. So the yellow area that's SA, it's going to be r over l times the whole disk area. So it's going to be r over l, and I'm going to use this formula, times pi l squared. In other words, it's going to be pi times r times l. So then now I'm going to go back to wanting this square root symbol. Pi times r times l is pi times r times square root of r squared plus h squared. There's my surface area equation. This is a hard problem. So I have two equations. I have a volume equation and I have a surface area equation. So we're going to do what we always do. We're going to use the volume equation to eliminate h. So I get that h equals 3v over pi r squared. I'm not going to use that number because I want to save, I'm not going to plug the number until the very end. Then I'm going to substitute that into this equation. So then I'm going to have surface area is going to be pi times r times the square root of r squared plus 3v over pi r squared squared. Now, what I want to do is I'm going to fast forward here because I have like 2 minutes. And if you simplify this, this can be simplified to the following expression. I'm going to bring, oddly enough, I'm going to bring that r inside. And it becomes r to the 4th plus 9v squared over pi squared r squared. It's a terrible looking formula. But I can ask the same sort of questions. What's the domain of this? Well, the domain is r greater than 0. The domain of the surface area equation is r greater than 0. I can't have a radius of 0, and I can have as big a bigger radius as I want. But if the radius gets really huge, that means I'm going to have a really large disk of paper, and it's going to have to be folded into a very shallow cone so it holds the right amount of water. Now let's think about extremes. As r gets closer to 0, this term gets huge. So the surface area gets huge. But as r goes to infinity, well, as r goes to infinity, this term gets close to 0, but this term gets huge. So the surface area also goes to infinity. So the first case, when r gets closer and closer to 0, that means I've got to have a cone that's very skinny. It's going to have to be really tall to hold enough water, and so it's going to end up having a large surface area. As r goes to infinity, the disk is going to be very shallow, but it's going to have a large area. So it turns out that we're going to have the same kind of situation that we had a while ago, that we know the extreme behavior of the surface area equation. R on the x-axis and the surface area on the y-axis, and we know that it goes up there and it goes up out here. We don't know what it does in the middle. So here we're finally ready to do the next step. We find the derivative of surface area and we set it equal to 0 to find out where these places are where it has these turning points. It turns out there's just one. So the strategy is find SA prime, set SA prime equal to 0, and solve for R. So that's the strategy. I'm just going to write that and then we're done. It turns out that finding SA prime and setting SA prime equal to 0 is not that hard. It turns out there's exactly one value of R that works, and that's got to be the min. Exactly one value of R causes SA prime to be 0. So it turns out it's not that weird. It's not a wiggly graph. It's just a graph that goes up on both ends and has one low point. So it's hard because of all this geometry, but each individual piece is not so hard, it turns out. All right, that's enough. I've kept you over time. I'm sorry. Thank you all. I'll see you Friday. Be sure to look at the course webpage for this information about the quiz.